In 2024, astronomers announced something remarkable. They found 30% of the universe. Not dark matter, that's still missing, still mysterious. This was regular matter. Atoms. Hydrogen, helium, oxygen, carbon. The stuff you're made of. For decades, we knew it existed. We could calculate how much there should be. But when we actually looked for it, counted stars, planets, gas clouds, galaxies, we came up short. 30 to 40% was missing. It was hiding in the most obvious place. The space between galaxies. Not empty vacuum, filled with gas. Hot gas, millions of degrees. Too hot to glow like normal hydrogen clouds. Too thin to block light from distant objects. Invisible. Until we learned how to see it. And when we did, we revealed something profound. Most of the normal matter in the universe, the atoms that make stars, planets, and you, isn't in any of those things. It's in the skeleton, the scaffolding, the cosmic web of filaments that connects everything. This is the story of the universe's hidden architecture, and why finding it changes how we understand cosmic history. First, terminology. When cosmologists say baryons, they mean normal matter. Protons, neutrons, electrons. The building blocks of atoms. This is distinct from dark matter, the mysterious stuff that doesn't interact with light. Baryonic matter is everything you can touch, see, measure directly. Stars, planets, gas, dust. You. And we know, from Big Bang nucleosynthesis and cosmic microwave background measurements, exactly how much baryonic matter the universe should contain. So astronomers conducted a census. Count the stars. Add up all the stars in all the galaxies. That's maybe 5% of the baryonic matter budget. Count the gas. Hydrogen clouds between stars. Nebulae, molecular clouds. Another 5 to 10%. Count the hot gas. X-ray emitting gas in galaxy clusters. Another 10 to 15%. Count dust, planets, black holes, everything else. A few more percentage points. Total. 60 to 70% of the baryonic matter we know should exist. 30 to 40% was unaccounted for. This wasn't a small discrepancy. This wasn't measurement error. We were missing a third of the normal matter in the universe. The calculations from the early universe were solid. The measurements of what we could see were accurate. But they didn't match. Either our understanding of Big Bang nucleosynthesis was wrong, decades of physics confirmed by multiple methods, or the missing matter was somewhere we hadn't looked properly. Somewhere invisible. Cosmological simulations, computer models of how structure forms in the universe, had a prediction. As the universe expands and cools, gravity pulls matter together, but not uniformly. Matter collapses into a cosmic web. Galaxy clusters form at the nodes, the intersections where multiple filaments meet. Galaxies sit along the filaments, cosmic highways of matter. Voids open up between filaments, vast regions where matter drains away. And in those filaments, simulations showed gas, lots of it, heated by gravitational collapse and shocks as it flows into the web structure. Temperature? 100,000 to 10 million Kelvin. Density? 10 to 100 times the average cosmic density. Still incredibly thin by Earth standards. Mere perfect vacuum. This gas has a name. The Warm-Hot Intergalactic Medium. WHIM. And it's in an awkward temperature range. Too cool to emit strong X-rays, like the gas in galaxy clusters at 10+ million Kelvin. Too hot to emit optical light, like the Lyman alpha forest, cooler hydrogen at 10,000 Kelvin. It falls in the gap between detection methods. In the ultraviolet and soft X-ray range, difficult to observe from Earth's surface, difficult to detect in space. The WHIM should contain most of the universe's baryonic matter, but proving it exists was incredibly hard. Finding this gas isn't just accounting, it's fundamental. This gas is where galaxies get their raw material. Matter flows along filaments, funneling into galaxies, forming stars. And when stars die, when black holes erupt, they blow enriched gas back into the filaments. The WHIM is the cosmic recycling system, the circulatory system of the universe. Without understanding it, we can't understand how galaxies evolve. Detecting the WHIM requires precision. The gas is hot enough to emit X-rays, but barely. Soft X-rays, low energy, easily absorbed by anything in the way. And you can't observe these wavelengths from the ground. Earth's atmosphere absorbs them. You need space telescopes. But even in space, the signal is faint. The X-ray background, diffuse emission from hot gas near the Milky Way, distant quasars, everything, drowns out the faint WHIM emission. Detecting it requires long exposure times, sensitive instruments, statistical techniques to separate signal from noise. For years, the best evidence was indirect. Astronomers used quasars, brilliant distant objects, as backlights. When quasar light passes through WHIM gas, atoms absorb specific wavelengths: oxygen, carbon, nitrogen, ionized by the hot gas. These absorption lines, dips in the quasar spectrum, proved the gas exists, but they couldn't tell us how much, couldn't map it, couldn't confirm it's most of the missing matter. We had pieces, glimpses, but not the full picture. Until recently. 2020s, a new approach emerged. Stacking. Combine observations of many galaxy pairs or clusters. Individually, each observation is too noisy, but stack them, add up the signals from dozens or hundreds of systems, and the WHIM emission emerges from the noise. It's like trying to hear a faint conversation in a crowded room. One person is inaudible, but if 100 people say the same thing simultaneously, you can hear it. The telescopes. eROSITA, launched 2019. German-Russian X-ray observatory scanning the whole sky. XMM Newton, ESA's X-ray telescope, providing high-sensitivity pointed observations. 2020 to 2024. These telescopes observed galaxy clusters and filaments with unprecedented sensitivity. eROSITA's wide field captured the large-scale structure. XMM Newton provided detailed spectra. 2024. Multiple teams published confirmations. Detection of soft X-ray emission from filaments connecting galaxy pairs. Measures of oxygen emission lines. The smoking gun. And when they measured how much gas was there, it matched. 30 to 40% of the universe's baryonic matter. Right where simulations predicted. The missing baryons weren't missing. They were hidden in plain sight. What does the cosmic web actually look like? On the largest scales, hundreds of millions of light years, the universe is a foam. Galaxy clusters at the dense nodes. Filaments stretching between them, cosmic highways. Tens to hundreds of millions of light years long. Voids in between, vast regions, 100 to 300 million light years across, nearly empty of galaxies. And filling the filaments, the WHIM, gas at 1,000,000 Kelvin, 10 times the average density, threaded with magnetic fields. The filaments aren't uniform tubes. They're dynamic, turbulent, complex. Temperature varies from 100,000 to 10 million Kelvin. Hotter near galaxy clusters where shocks heat the gas. Density 10 to 100 times the cosmic average. Still near vacuum by Earth standards, about 10 to 100 particles per cubic meter. Magnetic fields. Weak but pervasive. Generated by galaxy activity, stretched by cosmic flows. Composition. Mostly hydrogen, 75%, and helium, 25%, with trace heavier elements enriched by stellar winds and supernovae. This isn't just cosmic scenery, it's functional. Galaxies grow by accreting gas from filaments, cold streams and hot accretion. Depending on galaxy mass and environment, the filaments are conveyor belts. Matter flows in, galaxies converted to stars. Stellar feedback pushes enriched gas back out. This gas can recool, recollapse, form stars again. Or it can stay hot in the WHIM indefinitely. The cosmic web isn't static architecture. It's a living system. Matter circulating, galaxies breathing. Confirming the WHIM required multiple independent methods. 1. Stacked X-ray emission. Combining observations of many filaments to detect faint emission. 2. Absorption spectroscopy. Quasar light showing oxygen and other ions. 3. Sunyaev-Zeldovich effect. Hot gas slightly distorting the cosmic microwave background. 4. Fast radio burst dispersion. Radio signals delayed by passing through ionized gas. All 4 methods agree. The gas is there. Hot, ionized, filling the space between galaxies. The clearest evidence: oxygen emission lines. Oxygen 7 and oxygen 8. Highly ionized oxygen atoms, stripped of most electrons. This only happens at temperatures of 1 to 3 million Kelvin. Exactly the WHIM temperature range. When detected between galaxy pairs, it's unambiguous. That's WHIM gas. And the intensity matches simulations almost perfectly. Not just we found some gas. We found the predicted amount, at the predicted temperature, in the predicted locations. Theory confirmed. But questions remain. How do magnetic fields evolve in the WHIM? How much of the gas will eventually accrete into galaxies? How does feedback from supermassive black holes affect the WHIM? Answering these requires better instruments, higher sensitivity, larger samples. But the big mystery, where are the missing baryons, is solved. They're in the cosmic web, and we can finally see them. So the cosmic inventory is now complete. 5% of baryons, stars and stellar remnants. 10% of baryons, cold gas, molecular atomic clouds. 10% of baryons, hot gas in galaxy clusters, X-ray emitting. 5% of baryons, everything else, planets, dust, black holes. 30 to 40% of baryons, the WHIM. Warm-Hot Intergalactic Medium, the cosmic skeleton. Most normal matter in the universe isn't in galaxies at all. It's in the spaces between them. This changes how we understand galaxy evolution. Galaxies aren't isolated islands. They're nodes in a network, connected by filaments of matter. Gas flows in, stars form, supernovae explode. Gas flows out. Some escapes into the WHIM, some falls back. This recycling, operating over billions of years, determines what galaxies look like, why some galaxies are actively star-forming spirals, why others are dead ellipticals. It's about their connection to the cosmic web, how much gas they can access, how feedback affects them. And this connects to dark matter. The cosmic web traces dark matter's distribution. Dark matter provides the gravitational skeleton. Baryonic matter, the WHIM, galaxies' gas, falls into dark matter's potential wells. Without dark matter, there's no structure, no web, no galaxies. But without the WHIM, we can't see the web, can't trace where dark matter is on large scales. They're complementary. Dark matter is the invisible framework. The WHIM is the visible scaffolding. Let's zoom out. Put this in perspective. You're on Earth. Earth orbits the Sun. The Sun is one star among 200 billion in the Milky Way. The Milky Way is part of the local group, about 50 galaxies bound together by gravity. The local group sits within the local sheet, a flattened structure of galaxies. That sheet is part of a filament, connected to the Virgo supercluster, stretching toward the Coma cluster. And when you zoom out far enough, you see the web. Galaxies aren't scattered randomly. They trace filaments. And filling those filaments, the WHIM, the medium through which everything is connected. We're not in empty space. We're in the web. The Milky Way is fed by gas from the local sheet, material flowing along filaments. High-velocity clouds, diffuse gas falling into the Milky Way, may originate from the WHIM, accreting along cosmic flows. The Magellanic Stream, gas stripped from the large and small Magellanic Clouds, will eventually mix with the WHIM. Billions of years from now, when the Milky Way and Andromeda merge, the WHIM around us will heat and expand. A new node in the web. We're not separate from the cosmic web. We're part of it. And in the far future, hundreds of billions of years, the cosmic web will fade. Dark energy accelerates expansion. Filaments stretch. Galaxies lose contact. The WHIM will cool, thin, become undetectable. But for now, for the next trillion years, the universe is connected, alive, a web of matter, light, and gravity. And we've finally learned to see it. The discovery is just the beginning. Next-generation X-ray telescopes, like Athena, ESA, planned 2030s, and Lynx, NASA concept, will map the WHIM in detail. Higher sensitivity, better spectral resolution, able to detect individual filaments, measure temperatures, densities, compositions across cosmic web. And optical/UV observatories will complement this, tracing cooler gas, studying absorption lines in unprecedented detail. As observations improve, simulations will refine. Current simulations predicted the WHIM roughly right, but details matter. How much metal enrichment is there? How do magnetic fields evolve? How does AGN feedback affect the WHIM? These are next-generation questions, requiring data plus theory plus computation working together. And this discovery connects fields. Galaxy evolution, how galaxies get gas, how they evolve over time. Cosmology, testing Big Bang nucleosynthesis, understanding structure formation. Plasma physics, understanding behavior of hot, ionized, magnetized gas in extreme environments. Astrobiology, speculatively. If the WHIM fills space, do cosmic rays from distant galaxies propagate through it? Could panspermia operate on cosmic scales? The cosmic web isn't just beautiful structure. It's functional, dynamic, central to how the universe works. For centuries, we thought space was empty. Then we discovered interstellar gas, nebulae, the material between stars. Then intergalactic space, the void between galaxies. We assumed it was nearly empty, but it's not. It's filled with gas, hot, thin, ionized, threading through everything. Most of the normal matter in the universe is in this hidden medium, the cosmic skeleton, the scaffolding that connects galaxies, the circulatory system of the cosmos. In 2024, we finally saw it. Not directly, it's still too faint for that, but through clever methods, stacking observations, combining wavelengths, using quasars as backlights, we revealed the invisible architecture. And the universe looks different now. Not galaxies floating in empty darkness, but galaxies as nodes in a vast, connected web. Matter flowing, energy cycling, structure evolving. 30% of the universe was hiding in plain sight, in the spaces between everything. We found it. We mapped it. We understand it. This is Cosmic Canvas, where we reveal what's hidden. Until next time, look at the night sky and remember, the space between stars isn't empty. Neither is the space between galaxies. It's all connected, and we're part of the web.